What are LFP, NMC, NCA batteries in electric cars? NMC batteries. White heavy check mark pros. Higher energy density, more driving range. Faster charging performance in cold climates. Cross mark cons. More expensive, primarily due to lithium and cobalt. Shorter cycle life than LFP, higher thermal runaway risk. Uses environmentally unsustainable raw materials. Nickel-manganese cobalt, NMC, batteries are the most common form found in EVs today, ranging from the Nissan Leaf to Mercedes-Benz EQS. As the name suggests, the cathode end of the battery is typically composed of 33% of each nickel, manganese and cobalt. NMC packs are beneficial because of its higher energy density, more driving range, and is less sensitive to low temperatures, meaning it can charge faster in cold climates. But the use of cobalt and nickel are environmentally unsustainable, have been attributed to unsustainable and unethical mining practices in developing countries, and are expensive, making NMC packs pricier than LFP per energy unit. Car manufacturers typically recommend owners to only charge NMC batteries up to 80% to avoid long-term degradation effects. Some other automakers such as Polestar recommend a 90% limit. Full charging should only be occasional when needed during long road trips, for example. For specific charging recommendations from each manufacturer, check out our electric car model database. NCA Batteries. White heavy check mark pros. Higher energy density, more range. Doesn't use unsustainable manganese. Cross mark cons. Still expensive. Shorter cycle life. Nickel cobalt aluminum (NCA) batteries are similar to NMC packs and its prevalence is rare, only used in older Tesla electric car models such as the pre-facelift Model 3 sedan, Model S liftback and Model X SUV. NCA batteries have a high energy density but swaps the environmentally unsustainable manganese material with aluminum to improve its lifespan compared to NMC. But NCA packs still have a shorter life cycle and is more expensive than LFP batteries as it contains limited cobalt and nickel materials. Tesla recommends charging its NCA-equipped electric cars to 90% to preserve its long-term health. LFP batteries. White heavy check mark pros. Longer life cycle, less thermal runaway risk. Lower cost. More environmentally sustainable. Cross mark cons. Lower energy density, less driving range. More sensitive to cold temperatures. Still uses expensive and unsustainable lithium. Lithium iron phosphate, LFP, is emerging as a lower-cost, more sustainable battery type, crucially mooted as the battery to lower the upfront price tag barrier for smaller and entry-level EVs. It's already being used by the MG ZS EV and BYD Atto 3 crossover SUVs, base variants of the Tesla Model 3 sedan, Model Y SUV, and GWM Aura small hatchback. Unlike NMC and NCA, LFP batteries don't contain nickel, cobalt and magnesium, resulting in cheaper manufacturing costs. It's also more robust and less susceptible to thermal runaway compared to NMC. A key advantage of LFP is its longer life cycle, resulting in less degradation concerns. LFP packs are capable of more than 3000 full recharge cycle counts compared to NMC at around 1000 to 2000 cycles. It's worth noting that Tesla recommends 100% charging regularly on LFP-equipped models in order to properly calibrate the pack to show an accurate battery percentage indicator, which warrants the degradation hit due to the longer LFP life cycle. But NG suggests an 80% cap, so it varies by manufacturer. In some cases, an LFP-equipped EV with a 100% charging suggestion could have a similar usable driving range as an NMC or NCA vehicle limited by a 80 or 90% cap. For example, the mid-spec Tesla Model 3 long range with an 80% limited NMC battery would have the same day-to-day range as a fully charged LFP battery entry-level Model 3 rear-wheel drive RWD, which is $14,500 cheaper to buy, table above. Editor's note: Tesla recommends charging its NMC packs to 90%. However, LFP batteries are less energy dense, around 70% less than NMC, can't charge as fast in colder temperatures, and is still reliant on resource-limited and unsustainable lithium, which is rising in cost due to high demand. Other battery developments. Battery manufacturers such as Contemporary Amperex Technology Co. Limited, CATL, Panasonic, Samsung SDI, LG Energy Solution, and BYD are rapidly developing new batteries that are more energy dense, lighter, safer, more sustainable and, importantly, affordable. For example, all BYD electric cars use its proprietary blade battery technology, which uses LFP cells shaped in long, thin modules that are stacked closely together to provide structural integrity for the vehicle instead of using box-shaped modules. Due to this space saving, the Shenzhen automaker claims 50% more energy density and is said to be safer in extreme weather conditions and puncture tests. Similarly, Tesla is trialing its 4,680 cells based on a nickel-cobalt-manganese (NCM) chemistry on some Texas-made Model Y electric SUVs. The cylindrical cell allows for a claimed 5 times improvement in energy density, 6 times increase in power, and 16% increase in driving range. It is also part of the vehicle structure and cheaper to produce, around 56% cost per kWh claimed. Additionally, other developments include replacing graphite with silicon in the anode of lithium-ion batteries, sodium-ion batteries, which ditches expensive lithium for sodium in the cathode and electrolyte, and solid-state batteries that swaps liquid for a solid electrolyte to provide longer range, is significantly lighter, faster to charge, and more safer. Combined with innovations in vehicle design to maximize aerodynamics and more efficient electric drive units, new battery developments will ultimately evolve EVs for the better.